right, folks, it's Bass Action back in action. On this page of notes, we're going to look into a couple things. Our first example, we're going to look at using a given particular trig ratio and combining it with some other information with our all students take calculus to find maybe another ratio. Then we're going to start to look at our identities. Understanding the identities and being able to manipulate those well is going to be a key skill for those of you going on to calculus. It's going to be a very, very important skill for you there. So let's jump into our examples here. On example 1, just continuing our discussion about finding some ratios. So on our first example, it tells us that the angle we're working with is acute. So what we saw in the last video is that means that angle has to be in the first quadrant. Then it gives us a ratio, and I just want to talk about this one here specifically because the ratio it gives us is this 2 radical 7 over 7. And although we could just work with this exactly as we did in the previous video, what I want to call your attention to is the fact that we have a square root of 7 over a 7, which means the only way that I could have gotten this answer is if I must have rationalized this at some point. So what I'm going to do is I'm going to unrationalize this before I jump into my example. So if I unrationalize that, we can see what this problem must have looked like originally. So if this is my sine, then this is going to be my opposite, and this is going to be my hypotenuse. Again, you don't have to do this. It's just going to make the process easier for us, little smaller numbers. So I can draw that quick triangle like I did before, and my opposite will be 2, and my hypotenuse will be a square root of 7. So I can do a quick Pythagorean theorem. That's going to be a 7 equals 4 plus x squared. So that's going to quickly give me a square root of 3 here. So that gives me that side is a square root of 3. And then if I'm asked to find tangent, I'm just simply going to do my opposite over my adjacent. So I'm going to do a 2 over a square root of 3, and I'm going to rationalize that, and I'll get 2 radical 3 over 3. Okay, so that takes care of that one. Now on our next one, this is where we're going to actually start utilizing our all students take calculus. So on this next problem that I have here, I'm specifically told that my cotangent ratio, whatever it may be, is something less than 0. And what I can do with that is think about my coordinate plane here. And if I have my all students take calculus, if my cotangent is negative, then that means that there's no way that the triangle is here or here, and then which means that it has to be in one of these two quadrants. And then I'm specifically given a cosecant ratio that is negative. And if my cosecant ratio is negative, that means that I'm really thinking about sine. So of course, my triangle can't be here because if it was here, then my ratio would be positive. So that means that I'm going to draw my very quick sketch of a triangle in this last quadrant. So cosecant is going to be the hypotenuse over the opposite. So I'm going to put a 5 on my hypotenuse and a negative 3 on my opposite. And again, this is a quick Pythagorean theorem. In fact, this one's a Pythagorean triple, so I don't even have to write my Pythagorean theorem. I can just write a 4 there. That means I can jump into my cosine, my adjacent over my hypotenuse, and I'll get a 4 over a 5. All right, let's take a look at our next one. Again, we're given that this time our angle measure is more than pi. So now when I'm thinking about where should the triangle be, as I'm thinking about rotating around, I know that I have to rotate past pi, so that means that I can eliminate these two quadrants right here. If my cosine is positive, that means, again, my triangle is going to go into this last quadrant, and cosine is going to be adjacent over my hypotenuse, so this is going to be a 12, and this is going to be a 13. Again, we have another Pythagorean triple, so you want to be comfortable with that. So I'm going to put a 5 here, and it needs to be a negative 5. So if I'm asked to find cotangent, my cotangent is going to be my adjacent over my opposite. So my adjacent is going to be 12 and my opposite is 5 or -5, and I can put that negative anywhere I want. I typically like to write it a little closer to the numerator. Last one here that I'm going to work with on this type tells me that my sign ratio is going to be negative. So again, I'm going to go back to my all students take calculus. And if sine is negative, then I know there's no way that the triangle could be there or there. It specifically tells me that my tangent is 1. It's a positive 1. So I'm going to put that quadrant, my triangle, here in this third quadrant. Now, a tangent ratio of 1, that's actually a triangle that I already know. It's going to be my 45, 45, 90 triangle, or in other words, it's going to be 5 pi over 4 here. A couple ways we could get that. So I automatically know that secant, if I've been working with my practice quizzes, secant of 5 pi over 4 is going to be a negative square root of 2. So this one I didn't really need to draw the triangle, I just needed to figure out where it was supposed to be. All right, looking at some of my identities here, the reciprocal identities we've already talked about, so these you should be able to easily fill in. And just writing these might look a little different than what we've done so far. So if I'm thinking specifically about reciprocal identities, I want to think about how I can write sine using its reciprocal. So sine would be 1 over the cosecant of theta. Then that means cosecant theta is 1 over sine theta. Cosine is going to be 1 over secant theta. Secant is going to be 1 over cosine theta. You want to get comfortable moving back and forth between these because we're going to use these to manipulate and simplify expressions. Tangent, 1 over cotangent theta. Cotangent is 1 over tangent theta. And then, although we haven't used this a lot yet, up till now, we did mention it before that tangent can be expressed as sine theta over cosine theta. And cotangent theta then would be its reciprocal, cosine theta over sine theta. So just a little review, you'll want to be very, very comfortable with those. Now, Pythagorean identities. We've talked about this one before. Our basic Pythagorean identity right here, our sine squared x plus cosine squared x equals 1. It comes from our basic triangle. So if we look over here at our picture, the figure I have over here, we can review this idea. Sorry about that. Remember, this is a nice right angle. So if this is our unit circle, we know that this is a 1. And we understand that this is going to be my cosine theta, and this is going to be my sine theta. So just thinking Pythagorean theorem, sine squared theta plus cosine squared theta equals 1 squared, or just 1. Now, if we take this same equation, and I'm going to do it both algebraically and visually here. So if I take this same basic Pythagorean identity, and I'm going to divide the entire equation by cosine squared x. If I divide everything here by cosine squared x, each individual term will get divided by cosine squared x. It's going to simplify to sine squared over cosine squared. So from up above, we know that that's going to become tangent squared. Then cosine squared over cosine squared, that'll become 1. And then 1 over cosine squared, that will become secant squared. So we can easily manipulate the basic sine squared plus cosine squared equals 1 to get this new identity. Now we can actually see this over here in the picture as well. So what I want to call your attention to is the fact that this segment right here is also a radius of the circle. So if we're working with the unit circle, then this entire segment right here is a length of 1. The next thing that I want to call your attention to is that this segment right here is tangent to the circle itself, which means this makes a right angle. And since that's tangent, we can identify then that as tangent theta. So that's going to be this segment. Now, thinking back to our geometry vocabulary, when I look at this next segment in the triangle, if I extended this all the way through, it would pass through the circle twice, which means we can call this piece right here secant. So if I call this secant theta, again, I can see my Pythagorean theorem. My tangent squared theta plus my 1 squared, or just 1, equals my secant squared theta, and that's the exact same identity that we just got. Now, the last one that I'm going to do here, we won't be able to see it in the picture, but we can certainly still just manipulate it. What we're going to do is we're going to divide the equation by sine squared instead. So if I take this entire equation and I divide it by sine squared, and then I start reducing and simplifying, I get sine over sine. That's, of course, going to be a 1. Cosine over sine, moving on over, is going to be my cotangent squared x. And 1 over sine squared is going to be cosecant squared x. So these three equations are collectively called the Pythagorean identities, and you do need to be very comfortable with them, and you need to have these memorized.